Another topic that comes up in coding interviews is the minimum spanning tree of a graph. So let's say the nodes of this graph represent our offices, and their edges represent connection between these offices. Now let's imagine connecting these offices requires laying physical cables between them. The more cables we need, the more we have to pay. Now, how can we minimize our cost while keeping all these offices connected? It doesn't matter if they're directly or indirectly connected. Well, we can remove the edge between A and C. That's unnecessary because A is still connected to C via B, right? We can also remove the edge between B and D. What we're left with is called a spanning tree. So we have converted a graph to a tree. As I told you before, a tree is a graph without a cycle. Now, spanning trees are not unique. There are many ways to create a spanning tree for a given graph. So back to our original graph, we can also remove the edges between A and B and C. All our nodes are still connected, so this is another spanning tree. Basically, if we have n nodes in a graph, our spanning trees should have exactly n-1 edges. So here we have 4 nodes and 3 edges. The moment we add another edge, we form a cycle in this graph, and that graph is no longer a tree. If we have fewer than n-1 edges, not all of our nodes are connected. So a spanning tree should have exactly n-1 edges, okay? Now, each spanning tree has a cost, and that is the sum of the weight of its edges. So the cost of this tree is 12. What about the other spanning tree? The cost of this tree is 8. So this one is cheaper, and it's a better solution for reducing the cost of our cables. Now, there are algorithms for finding the minimum spanning tree of a graph. This is the tree with the minimum cost. In the next video, we're going to look at one of those popular algorithms called Prim's algorithm.